Welcome! In this video I'll show you how to solve problem 2.32 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. This problem asks us to determine the transmission coefficient for a rectangular barrier. So this is quite similar to what we have done before, but this time instead of having a potential well, we have a rectangular barrier. So our potential is plus V0 instead of minus V0. And we want to do this for three different cases: when the energy is less than the potential, when the energy is the same as the potential, and when the energy is greater than the potential. So the procedure, as I mentioned, will be the same that we used for the finite potential well. And as you might recall, what we are looking for is the relation between the coefficient f and a, right? The transmission coefficient is f over a modulus squared. That is what we are looking for. So what we are going to do is, again, the same as before. So this, don't get scared by this. We need to solve the Schrödinger equation for all three regions. Then we will, actually let me write it down. So solve, step one, solve Schrödinger equation for all three regions. Then we apply border condition. And then we solve for f over a. And that's it. That is it. That is what we have to do in this problem. It might look very scary, but this is the basis. Okay? Now let's build our wave function. So in region 1 and 3, there is no potential. So the Schrödinger equation that we need to solve is simply minus h bar squared over 2m, second derivative of psi dx squared, and this is equal to e psi. So from here, of course, we get our famous equation that we have solved many times over. This is minus 2m e over h bar squared times psi. And we can call this thing right here k squared. And thus our solution, our psi of x, will be some constant. Right? We have two possible solutions, so we have two constants here, e I kx plus b e minus I kx, right? We have seen this quite often. If you're unsure how to solve this, I do recommend that you take another look at what we did in the previous videos, because you have to be able to at least know which solutions to choose for the Schrödinger equation. So this is valid for regions 1 and 3. There will always be two traveling waves. One will be traveling to the right, one will be traveling to the left. So for region 1, we can just keep this. I'm gonna write down our wave function here in a piecewise function. So for region 1, we get this, and we have both an incoming wave, which is usually what we will be using if we are in a scattering problem. For example, we can send in some wave, some particle, and we will get some reflected, which is where this b part comes from. So this is in region 1, which is x smaller than minus a. In region 3, which is when x is greater than a, right, over here, in that region, we will have some transmitted part, or maybe not, right, depends on how strong our potential is, but we could have a transmitted part. So we will have some f e I k a, but we will not have anything traveling to the left, because how could we, right? The only reason why we have particles traveling to the left is because they reflected off of their potential, but we don't have any here. So unless we are sending in a particle from this side, which doesn't really make much sense, why would we send particles from both sides? That's a nightmare for any experiment. Then the other term, the one with the minus sign, is going to be 0. Okay? And finally, we need a wave function for region 2. However, there are three cases for the region between minus a and a. So for that reason, we will have to go look at each one of them separately. So let's begin with case number 1, e smaller than v0. So in this case, let's solve the Schrödinger equation. So our Schrödinger equation is going to be minus h bar squared over 2m, second derivative, and then plus v0 psi equal to e psi, right? As I mentioned, in the potential well, we had a minus sign here. Okay, now let's write this in a form similar to what we just had. So we write this as, let's put this to the right. So we get E minus V0. Then we multiply this by minus 2m over h bar squared and times psi. So the minus sign we can put in here. So we get, instead of E minus V0, we get V0 minus E. And there we go. Now notice, in this case, E is smaller than V0. And for that reason, this thing right here is going to be positive, right? So that means that there's not going to be any I coming anywhere. So we are going to define this thing as L squared, right? We can't really call it K again because it's not the same as before. That's a very, very, very common mistake. Okay, so don't be very careful, right? Pitfall alert. Don't call this just K squared. All right, so again, solving this using the method that I've used in previous videos, we get a solution of the form psi of x is equal to some constant times e to the lx plus d e to the minus lx. Okay, now again, if you don't know where this is coming from, you really should go back because you have to be able to at least know which solution to choose. So let's plug this in here. So for this particular case, when the energy is less than the potential, we get a wave function of the form CE plus DE minus LX. And this is step number 1. Now let me get rid of this part. All right, so as I mentioned, our procedure is step number 1, solve Schrödinger equation. Step number 2, apply border conditions. So let's do that. So what we need to do is apply border conditions to this problem. Now, what do I mean? Of course, if we are in region 1 and we go into region 2, our wave function must be continuous. It doesn't make any physical sense if the wave function just goes in here and suddenly it makes a jump and continues up there. That makes no sense. And also the rate of change of the wave function, right, its first derivative, that also must be continuous. If you're doing something like this, you can't just suddenly make a shift and go like, boop, upwards, right? The change must be smooth. So those are the two conditions. So let's apply them to point minus a. So continuity, both of the wave function and of the first derivative, at x equals minus a. So here we need that the wave function from region 1 evaluated at minus a must be equal to the wave function in region 2. So let me write it explicitly. So psi 1 evaluated at minus a must be the same as psi 2 evaluated at minus a. Okay, so that's what we're doing here. Let me just write it in a way that is readable. So there we go. So from this, we get a e to the minus ika plus b e to the ika. This is equal to c e to the minus la plus d e to the la. Now from the continuity of the first derivative, right, we get the psi 1 evaluated at minus a dx has to be equal to the psi 2 dx at minus a. So from this condition, looking back to our wave function up here, we get, deriving this, we have ik ae to the minus ika. Then we get a minus sign ik b e to the ika. And this has to be equal to these derivatives here. So that would be L C E to the minus LA minus LD e to the LA. Okay, so here we have equations 1 and 2, but we still have to apply these conditions at x equals a. So let's do that. So from continuity at x equals a. Now, in this case, we have these two wave functions. So again, what we need is that wave function 2 evaluated at a has to be the same as the wave function 3 evaluated at a. So This is CE LA plus DE minus LA has to be the same as FE to the I KA. And now from the condition for the derivatives, the first derivative of the second region evaluated at A must be the same as the first derivative of the wave function in the third region evaluated at A. So from this, we get that LCELA plus, sorry, not plus, but because we have to take the derivative, so we get minus LD e to the minus LA has to be equal to IK times FEIKA. And these are equations 3 and 4. Okay, now our goal is to take these 4 equations and find F over A squared, because this is T, right? That's our objective. This is our goal. So we need to get rid of C, D, and B, okay? If we wanted to find R, for example, we would need maybe like B over A or something, but that's not what we want right now. So how can we possibly get rid of C, D, and B? So let's now take a little look at this. We could think of maybe we have CELA here, CE minus LA, so that's not all that easy. We have BEIKA and BEIKA. So something we could do perhaps is write this B into this equation. So from equation 1, put it into equation 2, and that would eliminate B. So let's begin with that. We're gonna move up a little bit to have a bit more room. So we want to now put equation 2 basically, or actually let's do it step by step. So let's rewrite equation 1. So BEIKA, this is CE minus LA plus DELA minus AE minus IKA. And we want to plug this, so plug this into equation 2. So by doing that, we get IKA e to the minus IKA minus IK times this thing. So we get CE minus LA plus DE to the LA minus AE minus IKA, and this has to be equal to L CE minus LA minus L DELA. Okay, so here we have now eliminated B. We can, of course, factor some of these things together. So notice we have this minus IK minus AE minus IKA, so we get 2 IKA e to the minus IKA. And now let's put C and D to the right hand side. So upon doing this, let's see, we have C factor of, it has minus IK, but we are going to add it, so it becomes positive. So we get plus IK, and we have this e to the minus LA on both of them, so we can factor it out. And then we have L, so we get IK plus L times e to the minus LA. And now factoring out D, what do we have? So this will be positive, which will be IK, and then we have minus L e to the LA. So we can now divide by IK. I'm gonna write the 2 a bit closer here. So divide by IK, so this becomes 1, this becomes 1. And now this is L over IK, which we can also write, in case you prefer, as minus IL over K. And same here, this is L over IK, which we can write as plus IL over K. Okay, so now b is gone and we have a new equation. Let's call it equation 5. So let's go back to our other equations. Let's see, maybe there. And let's try to think how we can get rid of c and d. We haven't really used equations 3 and 4 at all, so perhaps we could do something there. So looking at those, we have CELA, CELA, DE minus LA, DE minus LA. So it wouldn't be unthinkable to try to, from here, eliminate C and D and then plug it into the other equation. So for example, something we could do, because we have minus LDE plus DE. So if we were to multiply equation 3 by L, so equation 3 times L, what we would get is C times L, so LC, ELA plus D times L, that doesn't look good, plus LD, E minus LA. This is equal to LFEIKA. And now if we add this, which is our new equation 3, if we add this and 4, take a look at this, we get 2 times LCELA, and then the D's cancel out, and then we have F factor of IK plus L and EIKA, which will be equation 6. So now we have found a way to write something which contains C. Now let's do something similar, but to get rid of D. So if here, instead, we multiply by L and then we subtract, right, instead of adding, so this comes from the new 3 plus 4, we can now say, which one do we want to subtract? So let's see, if we have these two, we do this, yeah, we can say equation 4 minus equation 3. Of course, it doesn't matter which one you subtract, you will have a minus difference, but you will still get to the same thing. Okay, so by doing 4 minus 3, now the C's cancel out, and we get, oh, I showed on the other, but it doesn't matter. I'll show you why it doesn't matter. So we get this minus this. So we get minus 2LD E minus LA. This is equal to, we get F factor of IK minus L EIKA. And we can now multiply all of this by minus 1, and we get the same as if we had done it the other way around. Okay, now we can simplify these just a little bit by dividing by L, so that this L here goes away as well, and we get plus 1, and this divided by L divided by L. Okay, so this is our equation 7. And now let's put it right next to equation 5. So I'm going to write down equation 5 here, or maybe just grab it. I'm going to grab it and move it. So this right here is equation 5. So these are our 3 new equations. And notice that we have an expression for C and D right here. Or, well, we almost have them. We have to do a little bit of simplifying. So we can divide by 2. So we get F over 2. And then we multiply by e to the minus LA. So e to the minus LA. And there we go. And similarly here, we divide by 2. And then we multiply by e to the LA. Whoops. So times e to the LA. Okay, and now we can plug in C and D into equation 5. So we plug in 6 and 7 into equation 5. So we get 2a e to the minus I k a. This is equal to C, but C is this thing. So F over 2 times, let's say, I like to have the 1 first, but it doesn't matter. IKL e to the IKA e to the minus LA. And now times the rest. So 1 minus IL over K e to the minus LA, which we can put right next to this one, right? We have 2 times that. Okay, now comes the d part. So we plug in d, so we get f over 2, 1 minus ik over L times 1 plus IL over K times e to the 2LA. Okay, so now we have an expression that only has f and a, and as you should remember, our goal, right? Our goal is to find f over a squared, which is t. So let's factor out f from the right-hand side. And let's see, what can we do? But I just want to make sure, did I do this correctly? Yeah, there's a teeny weeny mistake. I almost forgot to put this EIKA. So here, EIKA. There we go. Okay. So from the left-hand side, we have 2a, and we want f over a. So we can divide by this amount, or basically multiply by e to the minus IKA. So we get 2 of these, and we get rid of the IKAs on the right-hand side, just to make it a bit nicer. Then we have f over 2 factor of. Now we have to multiply these 2 parentheses, so we get 1 minus IL over K plus IK over L, and then we have this times this, the minus becomes a plus, the K's cancel out, the L's cancel out, and we get plus 1. And all of this times e to the minus 2LA. And then we have this other product here, where we get, once again, 1, and then we get minus IKL plus ILK, and then plus 1 again, because k's cancel out, l's cancel out, the minus turns into a plus with the I squared, and e to the 2LA. Okay. So there's a few more things to simplify here. We have, first of all, this is 2. So 2, this is 2. And now we could take this and basically multiply, right? Or take common denominator. So we have 2a e to the minus 2IKA. This is equal to f over 2 factor of. And now we have 2, nothing changed. But let's take common denominator between these 2 expressions. So plus here. So we can actually factor out an I as well. So plus I. I'm going to write this a little neater. So plus I. And then we get minus L squared plus K squared over K plus L. And all of this multiplied by e to the minus 2LA. Then we have this part where we get 2. And now we can factor out I as well. And we get L squared minus K squared. And all of this divided by KL. And all of this multiplied by e to the 2LA. Okay. Now this might not look like we have made much progress, but notice that these 2 things are basically the same. If we factor out a minus sign, let's say here, it doesn't matter from which one. Let's say that we factor from here, so plus, and this turns into a minus. Right, so I'm going to put it in red so we can see that we change this. Now we have the same thing in both of these. So we can now factor them out, and we also have 2 in both of them. So we get 2a e to the minus 2IKA. So my goal right now is to simplify this, because in principle this is already done, but this looks very messy. We could simply divide all of this and find f over a squared, but imagine squaring this. That's a nightmare. So this is f over 2 times, and let's see, now everything that has a 2. So we have 2 factor of e minus 2LA plus e to LA. And actually, let me write it like this, just to make it a bit more suggestive. So I'm going to write the positive one first. It's the same, right? It's the same, but I want this to be a bit more suggestive as to what will come next. Now we get plus I factor of L squared minus K squared over KL. So I'm going to take this part and this part, and we get a 1 from here. So we get e to LA minus e to the minus 2LA. There we go. And one more parenthesis. Does this remind you of anything? If it doesn't, let me give you a little hint. Or, well, actually the answer. Right, the hyperbolic sine of x is defined as e to the x minus e to the minus x over 2. And the hyperbolic cosine of x is e to the x plus e to the minus x over 2. So it's very similar to the regular sine and cosine, except that there are no i's involved. So looking at this, we can rewrite this as this over 2, but of course we need to multiply by 2 to compensate. And same here, so we divide by 2 and we multiply by 2 so that we are not doing anything illegal. And by doing that, so we have 2a e to the minus 2I ka equal to f over 2. Then we get 4 times, and this thing is cosine, so cosine or hyperbolic cosine of 2LA. And then we have plus I, this beast here, KL. And then this thing is the sine, the hyperbolic sine of 2LA. Times 2, right? I almost forgot, so 2I. All right. So now let's go for f over a. So f over a, let's see, let's not square it just yet. So let's begin with f over a. So we have to isolate this. So we take the a to this side, and thus on the left side we get 2 e to the minus I ka. Then we need to multiply by 2 again, so we get a 4. So 4 e to the minus 2I ka divided by this entire thing. So 4 cosine, the hyperbolic cosine of 2LA plus 2I times L squared minus K squared over KL sine hyperbolic 2LA. Okay, so now we can take the absolute value, the modulus. F over a. I mixed up a few things here. F over a. And why? This is t. Because we know that this is the same as the modulus of what is up here, right? The modulus of this divided by the modulus of what is down there. So for that reason, the modulus of this is simply 16, right? This is quite simple. The modulus of the exponential is 1. There's nothing to worry about there. And down here we have our real part and the imaginary part. So the real part of this will be 16 hyperbolic cosine squared of 2LA. And this part right here will be plus 4, right? We only take the part that goes along with the complex part. That will be plus 4 and L squared minus K squared over KL squared and hyperbolic sine squared of 2LA. And we can now simplify a little bit. So divide by 16, both numerator and denominator. So we get 1 and 1 there. We don't need to write this. And instead of 4, we get 1 over 4. And now we can use the notation that Griffiths like to use, for example, because we have 1 over this thing. So we can write this as t to the minus 1, right? T to the minus 1 is the denominator, which is cosine, the hyperbolic cosine squared of 2LA plus 1/4 of L squared minus K squared over KL squared hyperbolic sine squared of 2LA. But what is the hyperbolic cosine? The hyperbolic cosine squared of x, this is 1 plus the hyperbolic sine of x squared. So we can rewrite this as 1 plus, and now let's factor out everything that has a hyperbolic sine, and we get 1, right, coming from this one, plus 1/4 of L squared minus K squared divided by KL, and all of this is squared. But, just to make things simpler, we can take the 4 and plug it in here, right? And we get 2KL. And since this will be squared, we end up with a 4 that was outside before. And this is hyperbolic sine squared of 2LA. Okay, amazing. So now we only need to simplify what is in here. So for that reason, we take 1 plus, and now let's take common denominator. So we get 2KL squared, and let's expand this. So we get plus L to the 4th minus 2 times L squared K squared plus K to the 4th. All of this divided by 2KL squared. So 2KL squared. Okay, now notice that if we add this and this, we end up with positive 2KL. So we get plus 2KL squared. And we can now repack this. We can refactor it as L squared plus K squared. And this is squared and 2KL squared. So we made some progress, but we still need this L squared plus K squared and 2KL. So to find that, let's now go back to what L and K were. So we defined L squared as 2m v0 minus e divided by h bar squared. And we defined K, I don't think we did it explicitly, but we did it, when we solved the Schrödinger equation, as 2m e divided by h bar squared. And for that reason, of course, L is the square root of this. So 2m v0 minus e divided by h bar, and K is 2m e square root divided by h bar. So if we take L squared plus K squared and we square it, what do we get? Well, the e's will cancel out because we have 2me negative, 2me positive. So we end up with 2m v0 squared divided by h bar squared squared, so to the 4th power. And this thing is simply 4m squared v0 squared. Now, what about KL or 2KL squared? So this, well, it's basically K squared multiplied by L squared if you want to look at it that way, or you can take these square roots and square later, it's the same. So we get 4m e v0 minus e divided by h bar to the 4th power. So now we have to divide these two. So L squared plus K squared squared divided by 2KL squared. This is, this is squared, by the way. Let's see, we have v0 squared. This and this will cancel out this and this. The h bar will cancel each other out, and we will have v0 squared divided by e v0 minus e. Okay. So now we can plug this in here. So this entire thing is simply v0 squared divided by e v0 minus e. And there we go. This is the inverse, right, t to the minus 1 of the transmission coefficient. So 1 plus v0 squared e v0 minus e. And of course, t is 1 over this thing, right? 1 over t minus 1, right? But writing it as t minus 1 is a bit cleaner. So there we go. This is the transmission coefficient for the first case, right? When the energy was less than the potential. So now let's move to a second case where the energy is the same as the potential. So in that case, let's go once again for our wave function. So the first region is the same, a e to the I kx plus b e to the minus I kx. And now the second region, well, what is it? We need to solve the Schrödinger equation. So in the second region, we have minus h bar squared over 2m times the second derivative of our wave function plus the potential, which now is the same as E. So we get V0 psi equal E psi, but V0 is the same as E. So now these two cancel out, and we are left with d squared psi dx squared is equal to 0, right? Because these constants, they don't change anything. We can multiply by them and they are gone. And this is now super easy to solve. Integrate twice and we get psi of x is equal to some constant times some other constant times x. And this is our wave function, as simple as that. So c plus dx. This is, of course, for x between minus a and a. This is for x smaller than minus a. And region 3 is the same as before. So there we go. Now we need to, just as before, right? We just went for step number 1, which is solve the Schrödinger equation, right? Don't forget about it. It's the same procedure as before. Solve Schrödinger equation, apply the boundary conditions, and solve for f over a. And now boundary conditions. So at x equals minus a, we have that a e to the minus ika plus b e to the I ka. This has to be the same as c minus dA. All right, now the first derivatives. So we get that I k times a e minus ika minus ikb e to the I ka has to be equal to, now c goes away, it's a constant, we are only left with d. Okay, so these are equations 1 and 2. Now, at x equals a. So this time, we get, let's see, c plus dA is equal to f e to the I ka. And on the other side, now with the derivative, we get that d has to be equal to I k f to the ei ka. So these are equations 3 and 4. So now notice, again, we need to get rid of b, c, and d. So something we can see right away is from equations 1 and 3, we have c plus dA, c minus dA. So it seems rather simple if we take, for example, equation 1 plus equation 3, then we get ae minus ika plus b ei ka plus f ei ka. This is equal to 2 times c. And now if we take maybe 1 minus 3, we get the same thing on the left side. So a minus ika plus b e ika, and now minus f ei ka. And this is equal to now not 2c, but rather let's see, minus 2dA. So here we have expressions for C and D. So we would like to plug them into some equations where there was no B, for example, or something like that. Or we could maybe get rid of B from these very equations. So there's quite a few possibilities. All right, so now what we can do is we can put, for example, equation 4 into equation 2. So if we take equation 4 and plug it into equation 2, then what we get is ika e to the minus ika minus ikb e to the ika. This is equal to ik f e to the ika. Now this we can simplify, of course. We simply divide by ik. And there we go. We have something much, much cleaner. And something else we can do, for example, is take equation 4, which gives us d in terms of f, so that's super convenient, and plug it into this equation right here. So if we do that, so maybe let's call this equation 5, even though I don't think we're going to need equation 5, but you know, it's there just in case we do. So let's plug equation 4 into equation 6. So if we do that, we get a e to the minus ika plus b e to the ika minus f e to the ika. This is equal to minus 2a times, now equation 4, ik f e I k a. And now notice we have these two equations. If we add them together, so if we add 7 and 8 together, then we will get rid of b immediately. So we get 2a e to the minus I k a. We can put this on the right hand side if we want, and we can factor out f. So we get f e to the I k a factor of 1, which comes from here, but there's another one, so it turns into a 2. So we get 2 minus 2a I k. And we can do a few things. We can multiply through by e to the minus I k a, so we get rid of that exponential there. Let me rewrite this. It doesn't look good. So minus 2i k a. We can divide by 2. And well, now finding f over a is very simple. So f over a is simply going to be, let's see, we need to divide by this. So we get e to the minus 2i k a divided by 1 minus ai k. And now we need to take the modulus of this squared, right? Because t is the modulus of f over a squared. And this, well, the modulus of the complex exponential is 1. So we get 1 over, and now we have 1 plus a squared k squared. So finally, what we can do is plug in the value of k. So we know that k, as we saw before, or k squared, is 2m e divided by h bar squared. So there we go. This is the transmission coefficient. Or if you want to write it in terms of t to the minus 1, it's simply 1 plus 2m e a squared h bar squared. So this case was quite a bit faster and easier than the previous one. So finally, we have the case when the energy is greater than the potential. But thankfully, we don't really need to do anything in this case. Now, why is that? Well, that is because we have already solved this. Because in this case, what we are basically doing is that we have this barrier and we have now an energy that is greater than it. So there's basically no difference between the potential well and the barrier except for the sign of the potential, but everything else is the same, right? In both of these regions, the energy, so in this case and in this case, for the potential well and for the potential barrier, the energy was greater than the potential. So we are in the same situation. So for that reason, we could apply the same logic as before and do this entire thing, but we don't have to because we already did it. If you want to do it yourself, you can watch my previous video on this, and it's the same procedure. So we can take the result. So t minus 1, this is what we found. it was 1 plus v0 squared times 4e e plus v0. So this is before, okay, so I haven't changed it, so this is before, sine squared of 2a over h bar square root of 2m e plus v0. So the only difference is the sign of v0. So now all we have to do is change the sign of v0 to minus v0. Here it doesn't change because it is squared, so that you could get minus minus, which is plus. Now in the denominator, it does change, so it is e minus v0. And then we get sine squared 2a h bar square root of 2m e minus v0. And there we go. This is the result. So thankfully, we didn't have to go through everything again. If you did want to do it, the procedure is the same as before. So as you can see, these sort of problems are not really too hard. They can be a bit annoying algebraically because you have a lot of equations, but as long as you keep in mind what it is that you're trying to achieve, what it is that you want to solve for, this is not really all that bad. So I hope that this was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, maybe share it with some of your classmates who might be interested. And if you really like the content, maybe consider becoming one of my Patreons. You can start off with as little as $1, which is not much, but it really helps me out to continue pumping out content in the long run. So I hope you have a very nice day, and I'll see you in the next video. Thank you very much for watching.